Program BSc, subject Mathematics, semester 4th semester, session number 14, topic Evaluation of triple integral by change of variables, cylindrical polar coordinates. Here we can evaluate the triple integral by changing the variables in two cases. One is cylindrical polar coordinates and another one is spherical polar coordinates. So here let us see how to convert the Cartesian to cylindrical polar coordinates and how to convert the Cartesian to cylindrical polar coordinates and how we can evaluate triple integral by changing the variables. The change of variables in the triple integral. Already we have discussed the general form of a triple integral. A triple integral of f of xyz dx dy dz over r, and also we know that if f of xyz is equal to 1, then the integral is a volume integral. Now the triple integral f of xyz dx dy dz over r can be evaluated by changing the variables x, y, z to some new variables u, v, w, which are related to x, y, z. So, to evaluate such type of integrals, that is triple integral of f of x, y, z dx, dy, dz over r, we have to change the variables x, y, z to u, v, w. U and v, u, v, w are related to x, y, z. So, after to change Cartesian to this cylindrical, we should find out the Jacobian also. What is the Jacobian? Jacobian J is equal to dou of x, y, z by dou of u, v, w. That Jacobian should be non-zero. Not equal to 0 means non-zero. So, then the integral, triple integral of f of x, y, z dx, dy, dz over r is equal to phi of x, u, v, w. Phi of u, v, w means after changing the variable x, y, z to u, v, w, what will get a function that will be phi of u, v, w. That is, after changing x, y, z to u, v, w, what there exists a function that is in terms of u, v, w and Jacobian j, then dx, dy, dz changes to du, dv, dw respectively. So, after changing the variables x, y, z to u, v, w, the Jacobian should be find out, and Jacobian has to be non-zero, that is dou of x, y, z by dou of u, v, w, and the general integral, triple integral of x, y, z, f of x, y, z dx, dy, dz over r will be triple integral of a new function phi of u, v, w into Jacobian j, and dx, dy, dz respectively changes to du, dv, dw. The variables x, y, z vary in the region and the variables u, v, w vary over the corresponding region D. The variables x, y, z vary in the region and the variables u, v, w vary over the corresponding region D. That is x, y, z change. Next, let us consider a problem. Before that, let us see cylindrical polar coordinates. What are cylindrical coordinates and how to find out the Jacobian, and after getting the Jacobian and converting Cartesian to cylindrical, what will be the standard form? Here, let x, y, z be related to three variables r, phi, z by the relations x is equal to r cos phi, y is equal to r sin phi, and z is equal to z. The coordinates r, phi, z are called cylindrical polar coordinates. of the point x, y, z. Here r, phi, z are the cylindrical polar coordinates of the point x, y, z. Means after changing the Cartesian x, y, z to cylindrical, that is x is equal to r cos phi, y is equal to r sin phi, z is equal to z. What there exists a coordinate, it is r phi z. That is the coordinates r phi z are called cylindrical polar coordinates of the point x, y, z. X is equal to r cos phi, y is equal to r sin phi, z is equal to z. Now, the Jacobian J is equal to dou of xyz by dou of r phi z. So, what is that dou of xyz by dou of r phi z? It is a determinant of dou x by dou phi, dou x by dou r, that is cos phi minus r sin phi, 0 sin phi. Here the Jacobian dou of xyz by dou of r phi z is equal to dou x by dou r, dou x by dou phi, dou x by dou z. First row, dou x by dou r, dou x by dou phi, dou x by dou z. That is, when differentiating x is equal to r cos phi partially with respect to x, dou x by dou r cos phi, dou x by dou phi, or differentiation of cos phi is minus sin phi, dou x by dou z. In x there is no z variable and z is 0. Second row, dou y by dou r, dou y by dou r. To get dou y by dou r, differentiate y is equal to r sin phi partially with respect to r. That is, dou y by dou r is equal to sin phi. Next, dou y by dou phi, r constant, differentiation of sin phi is cos phi, r cos phi. Dou y by dou z, here also 0. Next, dou z by dou r. To get dou z by dou r, dou z by dou phi, dou z by dou z, differentiate z is equal to z partially with respect to r phi z. Dou z by dou r 0, dou z by dou 0, dou z by dou z 1. So after evaluating this third order determinant and simplification, after simplification we'll get r, that is cos phi into r cos phi, r cos square phi, minus sin phi into minus r sin phi, that is plus r sin square phi. We'll get r cos square phi plus r sin square phi. If we take our common factor, sin square phi plus cos square phi is equal to 1, and Jacobian J is equal to r. Now, the integral, triple integral of f of x, y, z, dx, dy, dz over r is equal to triple integral of phi of r phi z. That is, x is equal to r cos phi, y is equal to r sin phi, z is equal to z, is simply denoted as r phi z into Jacobian r dx, dy, dz, or respectively changes to dr, d phi, dz over d. Here d is the region in which r phi z vary as x, y, z over the region r. Let us take a problem. Evaluate triple integral of x, y, z, dx, dy, dz for the positive octant of the sphere x square plus y square plus z square is equal to a square by transforming into cylindrical polar coordinates. So here, by changing the Cartesian to cylindrical polar coordinates, we have to evaluate the given integral, which is bounded by the sphere, the region of the given integral bounded by the sphere x square plus y square plus z square is equal to a square. In the given region R is varies from 0 to a, because here in the sphere x square plus y square plus z square is equal to a square, r is a, r square is equal to a square, and r is a, the radius. So r is varies from 0 to a, and phi varies from 0 to pi by 2. Z is varies from 0 to a, where r, phi, z are cylindrical polar coordinates. Therefore, triple integral of x, y, z dx, dy, dz over r is equal to 1 by 3 integral of 0 to a, integral of 0 to pi by 2, integral of 0 to a, r cos phi into r sin phi into r z. We have to substitute x is equal to r cos phi, y is equal to r sin phi, z is equal to z. Therefore, x, y, z is equal to r cos phi, r sin phi, z. Jacobian r dx, dy, dz changes to dr, d phi, dz. Now first integrate with respect to r, then phi, finally z. When integrating with respect to r, integration of r cube, r power 4 by 4 sin phi cos phi, limit 0 to a. When applying the upper limit, a power 4 by 4, a power 4 by 4 integral of z sin phi cos phi d phi dz. Now sin square phi, integration of sin phi cos phi by using by multiplying dividing by 2. Here we have 1 by 3 into integral of 0 to a z a power 4 by 4 sin square phi by 2. Sin square phi by 2. Listen, it is not a sin square, it is sin 2 pi. Sin 2 pi by 2. In the previous step, we have 1 by 3 double integral of z into a power 4 by 4 into sin phi cos phi. Sin phi cos phi. Here to get sin 2 pi, multiply and divide by 2. That is 1 by 2 into 2 sin phi cos phi. 2 sin phi cos phi is sin 2 phi. So therefore, the next step 1 by 3 integral of z into a power 4 by 4 2 sin phi cos phi is sin 2 phi. It is not a sin square. Sin 2 phi by 2, limits 0 to pi by 2. Now applying the upper and lower limit, we will get 1, that is a power 4 by 8 integral of z dz. Integration of z is z square by 2. That is 1 by 3 into 1 by 8 into 1 by 2. A power 4 z square by 16. The upper limit a to the power of 4 into a square, a power 6. Their answer is a power 6 by 18.